Hello everyone, my name is Nicola. I'm currently in my first year of my master's degree in embedded software engineering at Politecnico di Torino. In the first semester of this year, we had a course about real-time operating systems, and we were asked to develop a project on RTThread to be presented to the professor at the end of the semester. This was for many of my classmates the first approach to developing using an RTOS, which can be challenging, and more so because we were asked to modify its kernel in order to obtain bonus points. The presentation of this project needed to be like one done to a client who asked for specific requirements. Our project was about developing a stress test for the real-time capabilities of RTThread using an STM32H7 development board by ST Microelectronics. We used the latest available version of RTThread and RTThread Studio, and we programmed using only the C standard programming language. Trying to abide by the rules of the MISRA-C standard. The board chosen by us was more than enough power and peripherals for what we needed, and was chosen mainly because we already had one, and so it was easy to program on one. We also used 3 sensors, a barometer and an IMU, communicating via I2C to the board, and a flash memory for data storage, activated asynchronously by 2 push buttons, one used to read the memory and one used to write it. In an initial design document, we proposed the usage of a Raspberry Pi Pico, which was substituted by the H7 because of better support. And we also proposed to use an SD card, which was later removed in favor of a flash memory, which was easier to use. The application had to sequentially read data from the IMU and the barometer, storing it in dedicated arrays. And this data was then processed by a benchmark. All the shared variables are obviously protected by mutexes to avoid concurrent access on the protected memory. The benchmark chosen was XenoJet Bench, which was initially conceived for multiprocessor systems and was then repurposed by us for a single-core real-time stress test. It is controlled by a main thread, which consumes the input arrays in 4 intermediate priority tasks created by the latter. The images show how the benchmark was initially conceived before being heavily modified, removing the true interest for the output values, because for our application they're of no interest, being our purpose just to stress the MPU. Substantially, the application presents a producer, a consumer, and an asynchronous task activated by a push button. Whenever one of these is activated, the task performs a write either the inputs or the outputs of the application to the first eligible address of the memory. If the flash memory is full, it is just erased. The priority of these tasks is like the one of the consumer thread, which is the actual benchmark, causing a round-robin alternation to take place. The other task is just the reading counterpart, activated by a second push button, and prints the read values to the console. As mentioned before, all the shared variables are protected by mutexes. which could cause long delays when taken because of the way they modify the scheduling. Real-time constraints had to be set, which for both producer and consumer means that they need to finish before the other task begins. And if they intertwine, the variables in the benchmark are updated mid-calculation, rendering the output unstable and causing issues on synchronization. A huge leap forward compared to the previous implementation, which used asynchronous tasks, was to find a way to handle aperiodic tasks in a predictable way. To do this, we designed a deferrable server defined as a more complex task, which uses two timers. The first one is used for the capacity of the server, and the other one for the period. If the capacity of the server runs out, its priority is modified and is set equal to the idle task. So the server will run if and only if there are no tasks to run at that time. The tasks inside the deferrable server are handled in a first-come, first-served rule. Thanks to the deferrable server, the asynchronous tasks are handled in a known and predictable way, strictly controlling the execution time. This way, the interrupt routines are also quicker because they just need to push the task into a list. This results in an enhanced running time, which is 15% shorter than before. Okay, now I'm gonna do a demo of the project, connecting the H7 board, and I'm running in debug mode, but I'll just let it run. Okay, the console opened. Now, if I run the project, all the peripherals will be initiated, and then the benchmark will start. The first thing that it will do is that it will read data from the MPU here and the barometer here. And when I press either this button or this button, the interrupt will be an interrupt will arrive in the system, and the H7 will run the deferrable server when the scheduler deems necessary. And here the system is reading the data from the gyroscope and barometer and accelerometer, and now it's restarted. The execution of Xenojet bench started. Now if I press this button, the interrupt will arrive in the system. The data has been written in the flash, and the benchmark just keeps going, and it will go on for 200 seconds at least, as I said before. Thanks to our many hours of work and study, we reached a full mark of 30 cum laude, which is the highest grade in Italian universities. For this, I want to thank Nicola and Fulvio, which are my teammates, and my professor Stefano Di Carlo from Politecnico. I also want to thank the RTThread team for the invitation to this event, and everyone in the audience for listening. I hope you enjoyed my presentation, and have a great day.